Periodic functions. A periodic function is a function that repeats its values in regular intervals, also known as periods. Due to this repetition, we can predict what will happen next based on what's happened prior. This is a very powerful type of function because when history repeats itself, it's good to help us figure out what might happen in the future. We'll look at several examples of periodic functions, and then we'll zone in on the ones that we plan to work on this semester. Let's look at some examples of periodic functions. So the first graph that you'll see here is a periodic function where one period is highlighted with the green. You can see that this graph is going to repeat itself as we move to the next stage. So it does the same thing over and over and over again, and we see it had done the same thing before. That's what makes it periodic. Let's look at a couple more pictures of some periodic functions. Here, we see some waves, and again, we start to see a pattern. You can see that there's a W shape here, and a W shape here, and when you look carefully, you see it's a repeated pattern. So therefore, that function is also periodic. Not all functions are easy to tell that they're periodic. Sometimes when you've graphed a lot of data, it's not always easy to see patterns. But if you look close enough, sometimes they begin to emerge. So here, if you look at this M shape, we can see that it happens again over here and over here. So from that, we can start to look at where the whole pattern repeats. And from there, we see a pattern that continues again and again. So that's another example of a periodic function. When studying periodic functions, there are two main things that we're really interested in that help tell us both about the function and about the predictability of what will happen later. The first thing that we're interested in is called the amplitude. The amplitude tells us how far the function goes from the center or midline of the function to the extremums, which is the maximum or minimum. Because the amplitude reports the distance we move above or below, it's directionless and therefore reported in absolute value. So the way we calculate the amplitude is to find the maximum y value of our function and the minimum y value of our function and find the difference between the two. We then take that number and divide it in half. You see the function formula written like this below, but we'll often write it as maximum minus minimum over 2, which means the same thing. So again, we're going to be looking for the maximum y value minus the minimum y value, and then we'll divide that in half. The other thing that we're really interested in is the period. So the period of a function is the amount of time or distance in terms of the independent variable that it takes to complete one cycle of the function. So we're going to be looking at the x values, and we're going to see how long it takes to start repeating our pattern. So let's go ahead and look at those periodic functions we were looking at before and see if we can find the amplitude and period for each of those. So our first example looked like this. To find the amplitude, we need to figure out the maximum value, the minimum value, and then we're going to take the difference and divide by half. So here, you can see that there's 1, 2, 3 hash marks. So the maximum value is 3, and down here, the minimum value is -1. So we're going to subtract those and then divide by 2. Be careful when you subtract a negative number. 3 minus -1 is going to give you 4. 4 divided by 2 is 2. So my amplitude here is 2, which means that if I were to draw a line directly through the middle of this function, which is not where the origin is, it's sort of here, I'll show you, the middle of the function, that from that midline, my function varies by 2 units in both directions. My period is how long it takes for my function to repeat. So what I need to do is find a starting point for my function and then figure out where it starts to repeat. And I can do this at any point on my function. So here, if I start here at this first blue dotted line after the green, I can see how long it takes to get to the point where it starts to repeat. So I'm going to go 1, 2, 3, for 5 units. So it takes me 5 x units before I start to repeat, so my period is 5. Let's look at the next one. Again, we start by considering the amplitude. How high and how low does my function go? Now this one is not as nice because it doesn't have the hash marks and it doesn't look like I'm going to hit an integer. So here I'm going to have to do a little approximating. So I believe that 3 is roughly where I've put this line. Therefore, I'm going to say that my maximum is approximately 2.5. And again, I'm using the approximation symbols because I'm really not sure exactly where it is. From that, I'm going to subtract off the minimum. So again, my -1 is roughly here, and I would say that's about halfway between. So -0.5, and then I'm going to divide that all by 2. So 2.5 minus -0.5 is going to give me 3. 3 divided by 2 is 1.5. So my amplitude here is 1.5. My period is how long it takes for me to start repeating my pattern. So I'm going to start with this point right here, which happens at x equals 0. And then I'm going to see how long it takes till I get back to this peak. So you can see here that this peak happens again at roughly 6. So it takes me 6 units to start my pattern again. So my period is going to be 6. Let's look at the last one and see if we can find the same thing for this last periodic function. For this last periodic function, again, I'm going to have to do some estimating about how high and how low my function goes. So it looks like to me that the highest point is on the first part of the peak of the m, and I think that that's at approximately 4. And then my lowest point down here in the repeated pattern, I believe is going to be -4. So 4 minus -4 all divided by 2 is going to give me an amplitude of 4. Now, my period is how often I repeat. So what I can see here is that I've started at 10, and then I'm going until right about here. So I have to come up with a pretty good approximation of how far past 11 that is. I think it's a little more than halfway. I'm going to say that it goes out to about 11.6. But remember, I'm starting at 10. So from 10 to 11.6 means that I'm going to have a period of 1.6 units. So again, this is an approximation. You may have come up with 1.7, 1.65. That's all okay as long as you're in the ballpark of what I estimated as well. So let's go ahead and look at the functions that we're going to be studying for this semester. There's 2 functions that are periodic in nature that we're going to spend a lot of time talking about to model the things that we're interested in. And these functions are the sine and cosine functions. We start by looking at the sine function. So f of x equals sine x is a periodic function that goes up initially. It starts off increasing at 0, and then it peaks at approximately pi over 2, and then it comes down and crosses through at pi, and then we'll get to a minimum at approximately 3 pi over 2, and then it finishes back at 0 to complete its period or its cycle at 2 pi. Sine has an amplitude of 1. It varies between 1 and -1. So if we do the maximum minus the minimum, 1 minus -1, that gives us 2. If we then divide by 2, that gives us our amplitude of 1. And we can see that our midline happens to be the x-axis here. And from the x-axis, our function varies by 1 in either direction. The period, or how often it takes to repeat, is going to be 2 pi. It's hard to see because 2 pi is an irrational number, so I'm going to label it here. 2 pi happens a little bit after 6, and pi is where it crosses through over here, which happens a little bit after 3. To find the period, you can either look starting at the origin and see where it starts to repeat to get you 2 pi, or you can look between the peaks, and that will also give you approximately 2 pi. So sine has an amplitude of 1 and a period of 2 pi. Again, the maximum value is going to be 1. The minimum value is going to be -1, which gives us an amplitude of 1. And then the period will be 2 pi. Now, cosine is going to have very similar characteristics. Turns out, sine and cosine are the same function shifted by pi over 2. So it's not a surprise that they have a lot of similar characteristics here. So the cosine function starts its journey at 1 when we're at the origin, and it starts off decreasing, and it hits its minimum at pi, and then it comes back up, and it ends its period at 2 pi. But again, the amplitude is going to be equal to 1, because here the maximum value will be 1, the minimum will be -1, so the amplitude is 1, which means it varies by 1 from the midline. And again, the period is 2 pi. So remember that pi is a little bit after 3, and 2 pi is a little bit after 6. It's a good idea to know roughly where those are, because sometimes you have to make a good approximation, and pi is a pretty good guess if you're dealing with something a little after 3. So again, if we're talking about the maximum, the minimum, and the period, the maximum value of cosine is 1, the minimum is -1, which gives me an amplitude of 1, and the period is 2 pi. So the first thing we want to talk about in terms of sine and cosine, our periodic functions, is applying what we already know to these new functions. And one of the things that we know how to do is graph transformations. So let's go ahead and look at that in this context. Example 1. Use graph transformations to draw and describe how f of x equals sine x changes for each of the following scenarios. So we're going to look at 3 different scenarios to see how the graph transformation impacts the function. So you can see the graph of sine of x graphed here, and we want to graph 6 sine of x. So remember, if we multiply a number in front, that's going to stretch our graph. So instead of going up as high as 1, we're going to go all the way up to 6. And instead of going down to -1, we're going to go all the way down to -6. But we're still going to go through the zeros in the same place. So that's going to give us a little bit of a map here on what our function is going to look like. So here we're going to start off increasing just like we were before. We're going to turn around at 6. We're going to come back down at pi, a little bit past 3, go all the way down to -6, come back up, cross through pi over 2, cross through 2 pi, and then we can also backtrack over here because we know we're decreasing down towards -6 on the other side. So we've taken every y value and we've stretched it up by 6 units. Our next graph is going to be to take 3 sine x minus 2. So we need to take the 3 to stretch the graph by 3 units, and then we need to shift the whole thing down by 2 units. So we can do this in 1 step or 2. Since we're pretty new to this, I think it'll be better to do it in 2 steps. So first, let's start by multiplying everything by 3. So again, when we're multiplying by 3, we're still going through the zeros, but now we're only going to go up as high as 3 for our maximum, and our minimum is going to be -3. So we're going to come up, down, up, and then again, down over here. So that's what the 3 does. If we now want to take this function and shift the whole thing down 2 units, what we need to do is we need to track the important points here and move them all down by 2. 1, 2, 1, 2. And so we're going to have the same exact graph as the red graph, but shifted down 2 units. So our final graph will look like this. Now, of course, you're always welcome to graph these on your calculator to see if you're getting the same thing that you're drawing. Let's try one more. Our final graph starts with sine of x again, and now we want to shift it by pi over 2 inside the argument. Remember that when we shift on the inside of the argument, we're moving things left and right. And this one is counterintuitive, which means if we're adding pi over 2, we're actually moving left pi over 2 units. So let's figure out what that means. So here, pi over 2 is going to be roughly here where the maximum happens. So that means if we shift it left by pi over 2, our maximum is going to move back over here towards the origin. All the other points are also going to shift pi over 2 to the left. So when we do this, something really cool happens. So remember, we're going to follow the path that would have started at pi over 2. So that was decreasing so it looks like this. And you may think that that graph looks familiar, and it should, because this graph is actually cosine of x. So by shifting sine of x by pi over 2 to the left, we end up with the cosine of x graph. So since we're going to be spending so much time working with sine and cosine, we want to consider the general form for these two functions. So the general form for sine and cosine are y equals a sine of bt plus c, and y equals a cosine of bt plus c. As you can imagine, if we're talking about sine and cosine without anything done to them, that means that a would be 1, b would be 1, and c would be 0. But we know that we can put some actions onto these functions to change what happens to them. So a is going to take our graph and either stretch it or shrink it. Because sine and cosine live between 1 and -1, that also means that if we multiply by a, that's going to change our amplitude to be a. So our amplitude is the absolute value of the number that multiplies in front of sine or cosine. Remember, amplitude tells you how much you vary from the midline. So amplitude is always reported as a positive number. We have to keep that in mind when we're thinking about our functions, that if we know the amplitude, it doesn't necessarily mean that the number in front was positive. The number in front could have been positive or negative, but we took the absolute value. The period of the function is normally 2 pi. So that means that if there's a different number inside of our function, we need a way to account for that. So our period is 2 pi divided by b. So here we can find out our b. So here we can find out our period by taking whatever number was put inside the function and dividing it into 2 pi. Our vertical shift is c. So remember, if you add or subtract something from the end of a function, if you add it, it moves the function up vertically, and if you subtract it, it moves the function down vertically. So even though we have all these letters as part of our general form, there are things we've been working with already in this course. So let's take a look at some examples. Example 2. Find a possible formula for each of the following functions based on their graphs. So here, what we're going to do is we're going to look at this graph and try to make a good judgment call about whether it's sine or cosine, and then from there find things like the amplitude, the period, and the shift. So if I look at this graph and I look at the shape of this graph, I really want to consider what's happening starting at 0 and ending at roughly 2 pi, because that's where my graph starts to repeat. So I can see that the period hasn't been altered here, because it goes from 0 to a little bit past 6, which is what sine or cosine does. Now, looking at the shape of this graph, it doesn't have the hallmark U shape that cosine does. So this looks an awful lot like sine. However, if I think back to what my sine graph looks like, sine starts off increasing and then decreasing. So what I notice here is that the sine graph has been rotated about the x-axis. And I know that in order to have a rotation, I would have need to multiply by -1. So I'm expecting something like negative sine x. So the other piece I need to consider is whether or not my amplitude has been changed. So again, I'm going to go ahead and find the maximum y value, which here is 3. And then I'm going to find the minimum y value, which is -3. And I'm going to divide that by 2. 3 minus -3 is 6. 6 divided by 2 is 3. So my amplitude here is 3, which means I would have need to multiply my sine function by 3 in order for it to be able to live between 3 and -3. Now, again, amplitude is reported as positive, so the amplitude is 3. But the function itself doesn't need to have a positive a. Instead, I need to look at the graph and determine if it was a regular sine graph or it had been rotated. Since it was rotated, the negative needs to go with my sine. So I'm saying that this is the function -3 sine x. You can check this by graphing that on your calculator to make sure it matches what you're seeing here. For the next graph, I'm again looking at what happens at x equals 0 and where and when it starts to repeat. So again, it looks like it goes until a little bit past 6, which for me means that the period hasn't changed. So I look at the shape of the graph between 0 and 2 pi, which is a little bit past 6, and it's got that U shape, that sort of drop, which is a shape that cosine takes on. So this is looking a lot like a cosine graph. So I'm going to use cosine as my starting point. So now I'm going to consider the amplitude. So again, I'm going to take the maximum value, which is 3, minus the minimum value, which is 1, and divide by 2. 3 minus 1 is 2, divided by 2 is 1. So my amplitude is 1. And here, it doesn't look like my cosine graph was rotated. So I'm pretty sure that my amplitude here is positive 1. I can write that in, or I could just leave it as cosine. Now, because my period didn't change, that means I don't have anything multiplying inside. And the last thing I need to consider is whether or not this graph was shifted. Now, the reason I'm asking if this graph was shifted is because it's not symmetric about the x-axis. In the last problem, my maximum value is 3 and my minimum was -3, which means it was symmetric about the axis because the maximum and minimum were the same number, but one was negative and one was positive. That's not the case here. The case here is that my function is living between 3 and 1. And so that tells me that my graph has been shifted up. So what I can do to figure out what my shift is, I can either reason through where my maximum needs to be, or I can use a shortcut formula. So if I'm going to reason through, I would remember that the maximum of cosine is 1. But now, looking at this graph, the maximum is 3. In order to get from 1 to 3, I would need to add 2, which means that my shift would equal 2, which means that my function would need to add a +2 on the end. However, there is a shortcut formula we can use to find the shift. The shortcut formula says takes the maximum value, which is 3, add the minimum value, which is 1, and divide by 2. 3 plus 1 is 4. 4 divided by 2 is 2. So this is slightly different than the amplitude because the amplitude looks at the difference between the maximum and minimum, and the shift looks at the sum of the maximum and minimum. But in both cases, we divide by 2. So this particular function, I'm going to say, is cosine x plus 2. Again, a good way to check this is to graph it on my calculator. Finally, let's look at this last graph and see if we can figure out what kind of function it is. So again, I'm going to start at 0, and I'm going to see where I start to repeat. So here, I see that I start to repeat a little bit past 3. That gives me a clue that it probably goes until pi, because pi is a little bit past 3. But that's different than the little bit past 6 that we've been seeing before. So that tells me that my period has changed. So that's something I'm going to need to consider. So I need to figure out if this is a sine or a cosine. Now remember, sine functions have 2 bumps in them, whereas cosines generally have 1 bump for each period it takes on. This one only has 1 bump. So I think that this is a cosine graph. Now, to find the amplitude of this graph, I'm again going to look for the maximum value, which is 4, minus the minimum value, which is -4, divided by 2. 4 minus -4 is 8. 8 divided by 2 is 4. So I know that I'm going to have a 4 in front of the cosine, but I need to figure out if it's +4 or -4. Since cosine usually starts at a maximum, and in this case it starts at a minimum, I'm feeling fairly confident that it was rotated around the x-axis, and therefore this should be -4 cosine. Now, on this one, remember that our formula for the period is 2 pi over b. And b is what we normally plug in to our function. Now, looking at this graph, I'm pretty confident that my period is pi because it ends a little bit past 3. So since 2 pi over b equals pi, I can solve for b. I can multiply this b up and then divide the pi down. And if I do that, algebraically, I get that b equals 2. So here, I'm going to fill in a 2 inside my argument. So I have -4 cosine of 2x. Now, I need to determine if it's been shifted. Again, I see that this function is symmetric about the x-axis. So it varies between 4 and -4. So the same number in the positive direction as the negative direction. And that tells me that it's not been shifted. However, if I use my shortcut formula, I can add 4 plus -4, which is 0, divided by 2. 0 divided by anything is 0. So my shift is 0. There's no shift here. So my function for this last one is -4 cosine of 2x. Finally, we have example 3. Here we have a word problem, and we want to figure out a way to take this word problem and figure out the associated function in terms of sine or cosine. So the example says, Boston averages 15 hours of daylight in June, 9.5 in December, and 12 in both March and September. Assuming that the number of hours of daylight varies periodically over a period of 1 year, write an expression for n, the number of hours of daylight, as a function of t time. Let t be in months, and t equals 0 correspond to the month of June. So there's a lot of information here. One of the most important pieces is that t equals 0 corresponds to the month of June, which means that when my function begins, the measurement begins in June. So I know that in June, I have 15 hours of daylight. So that means if I want to take a stab at graphing this function, when I start my graph, I'm going to start at 15. So when time equals 0, the daylight is 15 hours. So there's a lot of other information that I want to plot here, and that'll give me a sense of what my graph should look like. So let's see what else I know. In December, I have 9.5 hours of daylight. So December is going to be 6 months after June. So that's going to be t equals 6. So t equals 6 is going to give me 9.5. to go to 6. I'm going to go up to roughly 9.5. I think that's going to be about here. I also know that I'm varying periodically throughout the year, which means 12 months later, I'm back in June. I should be back up to 15. But I also know something about March and September. So March and September are going to have 12 hours of daylight. So March is going to correspond to 3 months after December. So that's time equals 9. So I'm going to go up to 12 and I'm going to draw on my dot there. And September is 3 months after June. So T equals 3. I'm going to go up to 12. And I'm going to draw on my dot there. So looking at my dots on my information, I get the sense that this is going to be a cosine graph, because if I connect these dots, this has a distinct cosine shape. If I had a sine graph, my original function would have been increasing to start, but instead it was decreasing to start, which tips me off that it's going to be cosine. So here I have cosine as my outer function here. And remember that my independent variable is time. So I'm going to have a t in here. And I had to figure out my amplitude, my period, and my shift. So let's start with the amplitude. So the amplitude, I'm going to take my maximum value, which appears to be 15, minus my minimum value, which is 9.5. And then I'm going to divide that by 2. So 15 minus 9.5 is 5.5. And if I divide that by 2, I get 2.75. And because this doesn't look like it was rotated, it looks like the general way cosine is shaped, I'm going to report that as positive 2.75. Now the period is 12 months, because after 12 months, the whole cycle starts again. So that means that my 2 pi over b is going to equal 12. So again, if I want to solve for b, I'm going to multiply the b up, and I'm going to divide the 12 down. So I'll get b equals 2 pi over 12, or b equals pi over 6. So that means that over here inside my function, I'm altering the period from 2 pi. And so I put in the pi over 6 to get my function to have the correct period. Now I have to figure out if it was shifted. This is certainly not symmetric about the x-axis. Instead, I'm varying between 15 and 9.5. So again, I can figure out my shift either by reasoning through it or using the shortcut. If I use the shortcut, then my shift is going to be the maximum plus the minimum, so 15 plus 9.5 divided by 2. So if I were to divide that out, I would get 12.25. And I know this is shifted up because normally I live between 1 and negative 1 with cosine. And if I multiply by 2.75, it would then live between 2.75 and negative 2.75, and this is much higher. If I add 2.75 to 12.25, I get 15, which is my maximum now, and corresponds to the information I have. So the function that best models this scenario is 2.75 cosine of pi over 6 times t, all plus 12.25. So being able to take information from a word problem and assign it to a periodic function is incredibly powerful, because again, this will help us predict what might happen at a later time. So this is something we're going to be doing out throughout this course.